Good morning. We're Team 3, consisting of Stefan, Fabian, Jonas, Capiche, Elvis, and Sriman. Today we'll be presenting our modular lift seat project, an innovative solution designed to assist individuals who experience difficulty standing. Here's a brief overview of what we'll be discussing today. First, we'll outline the problem that we aim to solve, then walk through our concept generation and selection process. We'll share details of our final concept, including engineering analyses, prototyping, and budget considerations, and conclude with a summary of our findings. Our project focuses on helping seniors, individuals with disabilities, and those living with chronic pain, anyone who really struggles to stand without assistance. Difficulty in standing up not only reduces independence, but also increases the risk of injury. Clearly, there is a significant need for a safer, more comfortable, and accessible solution. There are already some solutions available that mechanically lift users or provide a higher seating surface. However, these current products often come with significant drawbacks, such as high costs, heavy weight, difficulty in operation, and comfort issues. Recognizing these limitations, our goal is to create a more affordable, user-friendly, and comfortable alternative.
Problem definition needs statement. So pretty much, we're trying to design an affordable, adaptable wheelchair seat that assists users in standing up safely and comfortably. So we want to provide a gentle, controlled lifting to prevent any sudden propulsion, to prevent any accidents or injuries. We want to avoid raising the user too low, otherwise they won't be able to get assisted effectively and all the strain will be put back on their body. And we want to have a high weight capacity. So for our weight capacity, we want to support around up to 140 kilograms or 308 pounds. Problem definition, goals and objectives. So our goals for this project is to have a good affordability, at least one area with significant decrease. We want to have good accessibility, variety. We want users to feel comfortable using our product regardless of the utility. Adaptability. We want to make installation for the user to be user-friendly and easy, especially for elderly and people with disabilities so they don't struggle. We want the seat to be designed and installed and created for multiple seat types, no matter where you're sitting. User-centered design and testing. So we plan on gathering feedback from real users, possibly people who are elderly or disabled, to help refine the comfort, usability, and performance of the seat itself. Our objectives for this project is to be inexpensive, which we will measure in dollars. The model should be inexpensive since it needs to be easily affordable and accessible to people in need. For example, elderly who may not be able to work anymore, or people with disabilities who also would struggle for employment. Reduced operation time, which we will measure in seconds. The model should be able to easily and quickly lift people up and help them stand in an efficient manner to be actually useful in day-to-day scenarios. It can't take them like 30 seconds to a minute just to get them out of a seat, otherwise it won't really be worth their time or money. Reduced operation noise measured in decibels. The model should not be too loud and should be able to quietly lift users up without causing any other issues with the user's day-to-day. Reduced weight, which we're going to measure in kilograms. The model should be light enough to easily be transported by the elderly and the disabled. They should be able to move it around seat to seat and carry it with them. It shouldn't be that much of an issue for them. Problem definition, constraints. So first off, it should be comfortable. So 70% of users who use it must be incredibly comfortable using the seat. The user must be able to sit comfortably in the seat, otherwise the experience will not be enjoyable and they would prefer some other solution. Weight capacity. We want the weight capacity to be a maximum of 300 to 308 pounds, since it should be able to handle the user's weight comfortably and be able to lift them up without any issues in the future. And the seat itself must be able to rise a certain amount of distance and angle, so around 18 inches it should be able to rise at an angle of 25 degrees. So we want the seat to be able to rise and lift the user up to be able to help them stand. Otherwise, they'll just struggle to get out of the seat and the strain will be back on their body. Budget. The prototype must cost less than $600, since we want it to be able to fit within our team budget of $600, and to also be easily accessible to other people. battery operated, so we want the seat to be portable and modular, the lifting mechanism itself. Otherwise, the user will have to keep finding places to plug it in, and it'll just reduce the effectiveness of the product as a whole. And we want the seat to at least have a number of cycles raising and lowering before recharge. It should have a relatively long lifespan per full charge. Otherwise, they'll keep on having to rely on finding power outlets, external power sources, and it won't really be effective in helping solve the issue, which is just a good solution for getting out of seats. Reduce backlash to less than 1 inch. The seat should be able to not damage the user or hurt them when they try getting up. There should not be any noticeable force back to the user when it's operated, otherwise it will cause further injuries and just be dangerous. The mechanism should also be able to fit on a commercial design. The seat lift mechanism should be able to work with the testing seats and be able to easily be transported and attached to the seats. Otherwise, there's no use in even making the portable seat system.
Since there are a plethora of ways of getting this done, we've come up with our own different unique solutions to this problem. For my design in particular, I chose to make it essentially a spring mass damper system where the consumer will sit on the chair, which will be connected to a spring and a damper together in order to be able to compress it down to the seat location in question where this modular seat lift will be attached to. And then, as a result of potential energy, in this case spring potential energy, being formed, what will happen is once they release the mechanism with specific spring settings, what will happen is the spring potential energy will be converted to kinetic energy, and to prevent overshoot, what will happen is the damper will slow down their moving forward, thus preventing them from being injured, which is the last thing we want. The pros are that it's simple, it's economical, and requires no batteries because springs are fairly cheap and the damper can be made fairly cheaply. The issue with this, however, in order for this to be economical and not overly bulky, what will happen is it will be limited to the minimum weights of people. So it will be able to relatively well propel lighter people, but for heavier people, it may not be as well of a design put together. The issue also is that because of the damper involved in it, it will be fixed to a certain positioning, thus it may not be able to fully lift the person, thus it will work on the assumption that the person will be able to move by themselves somewhat, and it's idealized. This one does not take into account the internal friction as well as other variations that may happen as a result of the spring maybe not working quite as planned. In the case of Fabian's design, it provides more assistance, can be used on a variety of surfaces, and the middle actuator position can be adjusted to accommodate the weight of the user, where the design will use linear actuators to lift the person up. This, as a result, unfortunately means reduced load capacity. It also makes the cost higher due to multiple actuators, including a large one, and it has to be recharged periodically based on battery capacity, at least maybe once a day. Finally, the work of Jonas is such that it uses gears, in this case, to lift the person up, and it will use a battery to be able to lift them up as well. The pros is that it's SolidWorks compatible, so it's easy to design. It's steady, requires very little material, and has high torque capacity. But the issue is that it's very expensive also, and thus will be economically unfeasible for people who are poor, unfortunately.
So for my design, I went with a linear actuator setup that would be placed vertically at an angle so that user would sit on the setup with their back and a part of their hip. The help with this setup is that it carries less load for more weight, and that's one of the pros of the design. And it's also not bound by the type of seat it's used on, so it's much easier to use it on an office chair, a dining table chair, a toilet seat. The cons is that it can be more expensive than the alternatives, and it's bigger in size than the alternatives, so that puts a restriction on the design. For Elvis's design, it's a pretty simple design using a simple hydraulic system with linkages made of metal bars and a cushion. It would be placed on the seat and would be pushing vertically upwards. The pros of the design is that it's simple, easy to manufacture, and cost efficient. The cons is that double hinge design puts more stress on the hinges, so leading to easy failure, and it's carrying more load for more weight. For Sriman's design, it's similar to the lifting mechanism in mattress lifts. It's using linear potentiometer to track how far the lift has moved, and it can actuate the movement based on that. The pros is that it's easy to control with feedback and strong system can handle much more weight. The cons is that it's harder to implement since hydraulics are not available in a portable size and can get expensive pretty fast with the weight requirement. Coming from these, we came to a final concept design where we thought to use two adjacent seats together and which would be placed parallel, and uh, the seat would push off of the base seat at an angle, and this kind of setup would be placed at a a vertical angle at the chair so that it doesn't take all of the weight of the user. We realized that this design requirement has um, pros like it's carrying less load, modular for different seats, it's stronger and reliable mechanism, and it uses pneumatic switches to control how far the seat shoots off. The con is that it's less cost efficient and harder to manufacture. Iterating from this design, we realized that this design cannot adjust for the angle the person or the user is getting off of. So we moved on to a newer design involving a complete setup with a chair, and the chair design is much more refined and it can adjust for the angle based upon the user input and requirement.
The final concept. So our final concept consists of the mechanism attached to an already built chair. The pros of this concept is that it is stronger and a reliable mechanism, and it uses linear actuators, which allows for more control. And in our case, it would allow more control in terms of translation as well as rotation. The cons are that it is less cost efficient. The price of linear actuators tend to scale with its extension length, as well as it's harder to manufacture. You would have to purchase the linear actuators. And as you can see on the slide, on the left side you have the bottom dead center. On the middle you have a close-up picture of the linear actuator mechanism. And on the right side you have a picture of the top dead center. And in this slide we have a video of the final concept mechanism. And as is evident by the video, the mechanism allows for translation as well as rotation. So in the end, we selected the modular lift seat as our final concept, which balances functionality, affordability, and ease of use. And this design ensures greater independence for users while minimizing reliance on external assistance.
For the engineering analysis, only one side of the seat lift was considered to be able to create a 2D simplification. A load of 300 pound force was assumed for the calculations. In order to determine the maximum load, or the worst case scenario, the bottom dead center position was chosen because it puts the linear actuators in the most mechanically disadvantageous position. Therefore, the force to raise the seat will be greatest at that position. The angle of attack for the linear actuators at the bottom dead center position is 48.6 degrees and is indicated by phi in the schematics. The force on the actuator is around 451.25 pound force, which would be split between the two actuators on both sides. However, to keep a level of redundancies, both actuators are designed to carry the load alone, meaning that both actuators will be able to bear a load of around 500 pound force. Additionally, based on the CAD model, the stroke length of the actuators was determined to be around 9 inches. Moving on to the numerical analysis, the first part we will consider is the crossmember of the seat, the most critical part of the seat base. The finite element analysis shows that the part will not yield under the expected operating conditions. However, there are stress concentrations at both ends of the beam due to the sudden changes in geometry. This was mitigated but not completely removed by adding fillets. Next, the analysis of the arm had greater stress concentrations at the holes but still converged, and, when not considering the stress concentrations, the part will not yield under normal operating conditions. Similarly, the analysis of the slot produced the same results as the arm, showing that the part will not yield when not considering stress concentrations. Finally, the analysis of the side plate showed that this part will not yield under normal operating conditions either, and that the simulation converges. Based on this, all our most critical parts will be able to withstand the loads that they are designed for.
First prototype, we decided to utilize 3D printing. We first scaled down the entire assembly by 50% in order to save on print time and to be able to fit it within the print volume. The prototype took around 6 hours to print and consumed approximately 100 grams of filament or around $5 to $10 of material. Because small enough fasteners were not available to us locally at stores like Home Depot or Lowe's, and the lead time for ordering online through McMaster-Carr was too long, we decided to print a set of pins to fasten all the parts together. In this slide, you can see the concept prototyping images. We show the side panel with the hinge mechanism that's able to raise and lower the angle. You can see the top section. It lowered down to the base position and it maxed out to the maximum position. That's how we designed the concept prototype.
Budget analysis. So on the table, we have all the items that we would need for our concept. The first item would be the Pintorp chair, which can be found in IKEA. We would only need one of these, and the price goes for $35. We would also need two eye-end fittings, which could be found in McMaster-Carr, and they tend to go for $2.22 each. We would also need two heavy-duty eyelet mounting brackets. These could be found in McMaster-Carr as well, and they go for $7.14 each. We would also need two 90-degree eyelet mounting brackets. These could be found in McMaster-Carr, and the price tends to go for $6.32. And we also need several screws and nuts. Because these tend to come in packets, we've just included the price of the packet. We don't need all the nuts and bolts that come in this packet, but for the sake of simplicity, we just included the price of the packet. So we would need the 1/4 inch medium strength grade 5 steel hex head screws. These can be found in your local hardware store. In our case, we found them in Home Depot. We would only need 4 of these, but the price of a packet is $11.29. We also need a 1/4 inch steel hex head screw for wood. These could be found in your local hardware store. We only need 4, however, packets run for $10.26. Lastly, we need the 1/4 inch medium strength steel hex nuts. These could also be found in your local hardware store. We only need 8, however, packets tend to run for $7.08. In total, our mechanism would cost $94.99.
Overall, the best design includes linear actuators, seat motion support for moving, as well as guiding links so the seat moves appropriately. The numerical calculations show it's possible to move the seat forward and up if there are guides to help it move in a linear manner, and the force of the linear actuators that would push the seat would and should be greater than the maximum force that the seat can handle, which is about 300 pounds.